to make sure everybody got the message I put on Moodle, here's Corsa. The problem with the site for the reading quizzes is that we need to renew our downloading of the web pages. It's a browser cache issue. So if you get that error when you try to go to the reading quiz, just do Shift Control R and it should then work. So I put a message on Moodle for it. I did extend the due date for that until 11:59 tonight because a lot of you weren't able to do it all night because of those problems. And not knowing what the problem was, didn't think about clearing the browser cache. Everybody understand? All right, moving on. We're going to talk about eddy currents and inductance today. And so I have a picture here of a transformer. It's more than meets the eye. And we'll learn how the transformer works by the end of today's lecture. First, a couple questions relating to the lecture yesterday. What will not produce a magnetic field? Hopefully now I have things straightened out. Well, let me... You put rotating. Okay, we have 3 people who haven't answered yet. Everybody's in except for the one who acknowledged she's still working on it. It doesn't matter. All right. 114. Hey, didn't delete my answers for me. I'm always excited when something works. So 14, the large majority here, answered a moving wire through a constant magnetic field. We had, my mind, of course, just going blank. I feel idiot when James, and I can't remember your name, just asked, does it matter the orientation? If it's just a wire moving through the magnetic field, its orientation isn't going to matter because it's not going to produce a magnetic field, right? You will have an electric field produced, sure, if it's oriented the right direction, but you won't have the magnetic field except for when you change the velocity. And that's why I changed the last one to rotating, as I talked about yesterday. If it's rotating, then you're changing magnetic flux through the coil, and it's definitely going to induce a current, and according to Lenz's law, it'll be creating a magnetic field opposing the change in flux. So, the follow-up question, what is Lenz's law? So one of these statements should be the correct one. Perica and Corso. Okay, everyone's answered 2400 and whatever the balance is, I can't see it. 19 minus 6 is 13, I guess. Okay. I'm going to make things tough on Corso. So really, do you have to make them tough on me? So Corso, my man, we had 13 people who gave the correct answer. An induced EMF acts to oppose the change in flux. What I just said before we had the question. We only had 2 people who said the first one. But the first one is an important statement, but it's not Lenz's law. So what is that first one?
I didn't say the first one.
Yeah, I know. I said I was going to make it tough on you. What is that first statement? I mean, I didn't know that you hadn't said it. I assume, How could you know that wasn't the right answer if you didn't? Okay.
I mean, I still have 20% chance to guess.
Let's just go with whose law is this one right here? Okay. Did you answer? No. Okay. The answer is what other people have been saying. I couldn't tell if you said it or not. Faraday's law says that a changing magnetic flux produces an EMF. Faraday's law was, let's start with the EMF. The EMF is equal to minus the change in magnetic flux over change in time. And I said this minus sign is to remind us to look at Lenz's law to determine the direction. Now, in a technical sense, it's for you define a certain direction by a convention and it has a meaning there. But for our sense, it just reminds us to look at Lenz's law to determine which direction current would flow. So Lenz's law combined with Faraday's law allows you to answer what's going to happen in a generator. So a review of what we've learned in electromagnetism. We learned, first of all, that there is a force between charges. Very simply, if I have 2 charges and they're both positive, what kind of force do I have between those positive charges? It's a force that's pushing them away from each other, a repulsive force. What if they're 2 negative charges? Again, repulsive. What if one is positive and one is negative? Then they're attracted. So with electric charges, we had opposites attract, likes repel. Then we went on to electric fields. The purpose of the electric field was to make life easier in calculating the forces due to a charge in the presence of a collection of charges. That was the purpose of the electric field. It's a force field to make it easier to calculate the force on a charge. And so that electric field was defined as the electric field vector is equal to the electric force, that's a F with a vector sign over it, divided by charge. Those are 2 basic things, and then we got to magnetism. And in magnetism, we learned that there were, just like with electricity, 2 poles. In electricity, we called them a positive and a negative pole. With gravity, there was only 1 pole. We just called it mass, and positive always mass. With magnetism, instead of going with positive and negative, the minds at hand went with north seeking and south seeking, north and south. So we have 2 poles, but we call them north and south. Just like positive and negative, they're opposites. And just like positive and negative, opposites attract, likes repel. So north is attracted to south, north repels north, south repels south. So we have a kind of an analogy here between the magnetic force and the electric force. But as I told you at the beginning of magnetism, we are never going to actually talk about the force between 2 magnets. We only talk about the force between a magnetic field and something. So then we have the idea of the magnetic field. That is, magnetic field goes out of north and goes into south. And there's always going to be a torque to make things align with the magnetic field, because opposites attract and likes repel. And then if you have a moving charge, that's when things get really interesting. Because a charge that is stationary is not affected by a constant magnetic field. If I just put an electron and have it sitting stationary on the earth and the magnetic field is constant, there's no force due to magnetism on that charge. But as soon as the charge starts to move, then I can have a force. But the force is a little more complicated. The force on the charge is not QE like it was for electric field. It's QV cross B. So we have that cross product. Cross product means we're multiplying perpendicular parts. So if I have an electron that's moving parallel to the magnetic field, there's no perpendicular part, hence no force on it. But if it's moving with a component that's perpendicular to the magnetic field, then there will be a force that will make it spiral around in loops. So moving charge creates a magnetic field. That's our next step we learned. I did the demonstration yesterday from Ørsted's original happy coincidence, serendipity, of finding that when he plugged in his equipment, the compass moved, and thus there must be some kind of magnetism produced when you have a current flowing. And then we went from that current flowing to seeing things like this, where we have loops of current flowing to make a much stronger magnetic field. And then I put in this this core that's a magnetic permeable material, it's iron, that made the magnetic field much, much stronger. So we can make magnetic fields by having moving charge. So an electromagnet, this is an example now of an electromagnet, is made by just having current going in a loop around something with a large magnetic susceptibility, so it amplifies the magnetic field. And then finally, we had Faraday's law of induction and Lenz's law, that a changing magnetic flux will create a voltage difference that acts like a battery, hence the term EMF, and Lenz's law tells us which direction it's going to be. Now some really fun demonstrations. One that I'm going to show you right here. This is a tube that, quite frankly, I wish was a little bit larger in diameter and a lot longer. I used to teach at PHYS, you probably know, and there my physics classroom was 2 stories at the front, and it had a little walkway, and I had like 10-foot pipes that I used for this, much more dramatic. So I have here 2 things that look the same. They're not the same. This one has no effect from that iron. This one clearly does. So what's the difference between that one and this one? That one's a magnet, this one's not. Now, this is a copper tube. Magnetic properties of copper? None. So there's no attraction between the magnet and the tube. Now this demonstration requires a second person. Will somebody come and help out the old man? Okay, Ashley, come on up. Now, it's kind of tricky. I'll try to do the hard work today and have you do the really easy thing. You're just going to put your hand about 3-4 inches underneath here to catch it. I'm going to try to drop this down the center and have it so it's hanging straight down. If it hits the sides, it will roll on the sides and you'll hear it. Okay, went straight through. That's the way it's supposed to work. Life is good. I'm going to do it again. If I can do it twice in a row, we're great. That was not quite as good, you heard it, but it still came through pretty quickly. Change to the one that has a magnet. Do the same thing. Okay, it didn't go. That's a really bad drop. Now it's going down. What happened there? Went really slow. Let's try it again. Science, right? We got that whole scientific method. We observed something really interesting. So next we have to come up with a hypothesis that explains why this observation occurred. So if you're in lab, your observation is, I noticed that when you put the non-magnetic slug down here, it just fell right through quickly. But when you put the magnetic one through, it fell slowly. And then you're like, why? Right? Hypothesis. So why? Something about resistance?
Like, not resistance, but a different thing that is like making it not as magnetic.
Do you have something, Erica?
I was thinking because of like when it gives out, I guess like it slows it down because it even though it doesn't stick to this one, it still has some charge, I guess. Just a little bit.
Any other ideas?
You know, if it's attracted to the magnetic, there's other forces going on other than just the one that.
The other forces than just one going down. We can explain all of this by using two things. Well, three things really. Faraday's law of induction, Lenz's law, and then finally, how two magnets interact. So I have the magnet going in here. So we have this tube. It has an area on it. So let's just say I start with it above the tube and I bring it down. What's happening to the flux, the magnetic flux, as the magnet gets closer to the tube? It's doing what? Staying the same, increasing, or decreasing? I will draw a picture. Here's the opening. Here's my magnet. Magnetic field lines come, oh, come on. Magnetic field lines come out of north and go into south. So as it gets closer, what's happening to the field lines where that purple circle is? You're getting the field lines closer together, which means stronger. You have more magnetic flux, right? Because the magnetic field going through the opening of that circle is getting bigger. So as it falls, magnetic flux below the magnet increases. Now, if the magnetic flux increases, according to Faraday, what's going to happen? That's right. It's going to produce an EMF. Now, I say EMF, you said current, I said right, and now I said EMF. It's going to produce an EMF, which means it's going to behave like there's a little battery. So it's going to behave like we just inserted a little battery on this. Now I just put a random direction. Let me erase the last line so it doesn't have the positive side. How do I determine which side is going to act like the positive side for that little battery? I have Faraday's law says I have an increasing flux, so I'm going to have an induced EMF, an induced voltage. How do I determine what direction the current that results from that induced voltage is going to be? It's going to go the direction opposing the change in flux. So the magnetic field is getting stronger, so it's going to oppose the magnetic field to oppose the change. So that means the induced magnetic field, since that's pointing down, the induced magnetic field is going to point up. So I take my right hand, point the thumb of my right hand in the direction of the induced field. So I put my thumb of the right hand up, wrap my fingers, and I can see that the current is going to be this side that has the battery is supposed to be the side closest to me. It's going to be going like this. So the current is like that. So the current goes into the negative and out of the positive. And it's going to make an induced magnetic field that's opposing the change in flux. But now we look at that, we have the falling magnet had north down. I'm creating an induced magnetic field with north up. What kind of force do I have between north and north? It's a repulsive force. So that's going to create a repulsive force between this current loop that was created in my tube and the falling magnet. That was what's below. What about what's above? As the magnet is dropping away, if I have the loop up here, what's happening to the magnetic flux up there? It's decreasing. If the magnetic flux is decreasing, then Lenz's law says the induced magnetic field is going to try to oppose the change. Do you have a question? No? Okay. You were just...
Yes.
Okay. I just want to be attentive to my students. So it's going to have an induced current to oppose the change. If the magnetic field is decreasing, to oppose the change, we need to have our induced magnetic field the same direction. So above, where the magnet is moving away from, the induced magnetic field is going to be pointing like this to oppose the change in magnetic field. But that's the same direction as the magnet had. So now we have north pointing down to south. What kind of force do we have between north and south? Attractive. So that means that the piece of the tube that's above the magnet is pulling it up. It's attractive. The piece of tube that's below the magnet is pushing it up because it's repulsive. So we have a force that's pushing up on the magnet from both down below and up above. And so that's why it comes down slowly. Now, why does it come down at all? Because I have no change in flux if it's not moving. As soon as it moves, I have a change in flux, and I have these currents going around in circles. We call them eddy currents because eddies are going around in circles, like whirlpools or eddies. So we have these eddy currents that occur because of the change in flux, because it's falling. The faster it falls, the bigger the eddy current, and so the upward force needs to match the downward force for constant speed, so it will fall until it reaches the speed where the upward force matches the downward force, and then it reaches terminal velocity. This is great. It's great for a number of reasons. Number one, we like amusement park rides. You guys are all young. You ride on a roller coaster, one of the things they need to have is brakes. Make sure that you slow down at the end and don't crash. If the power goes out, you want those brakes to still work in some fashion. So some roller coasters use eddy current brakes. They basically have magnets on the cart, and when you get to the end of the track, it puts a piece of metal that's conducting, but not magnetic, between the magnets, and you have eddy currents that create forces to slow it down. So whether you have electrical power or not, as soon as that piece of metal is between the magnets, it starts slowing down, puts a brake on there. And so that's something that's used. If you buy an electric car, the electric cars get better economy in city driving than they do in freeway driving, because in city driving, you're doing a lot of starting and stopping. So you use energy from your battery to get the car moving. But you don't get up to high speed and then you brake to stop. Well, it uses a generator, which really eddy currents are the same idea as a generator. You're just creating the eddy currents in something you can recover it from. And so they use brakes that are actually generators. So when you're braking, you're recovering the energy. So in city driving in an electric car, you expend energy to start, you recover energy to stop, and the total amount of energy you lose is pretty small. Hence, hybrids and electric vehicles are great for city driving. Freeway driving, not as much, because you're going high speed, you're primarily losing energy to air resistance. You can't recover that energy. So those are eddy currents. Here's other examples. If I have a magnet and I have a pendulum with a conducting material, then it will slow down considerably. If I put a pendulum that has slits in it, those slits won't let it form circular eddies of reasonable size. And by not being able to form circular eddies, you don't have the eddy currents, you don't have the resistance. So back to this demonstration from yesterday. I threw a ring, you saw it work. I'm going to put this here, another non-magnetic material. We can now check and see what's non-magnetic. Non-magnetic, non-magnetic. This is also non-magnetic. So I put this ring, but it's split. When I plug this in, what should happen now? I want to hear some predictions. I have two rings, one that's split and one that's not. Brandon, what's going to happen?
The split one will not go as high as the one that is continuous.
Okay, Brandon says the split one will not go as high. What's your reasoning?
It's not the closed continuous current.
Okay, so now that we have somebody who is brave enough to think it through, now we can do it. Thank you. That was an uncomfortably long silence. Was he right? What do you say, Brandon? Were you right? Yeah, for the most part, except for when he said not as high, what should he have said? Not at all. Because how much current do you have going across this gap? None. So it doesn't make any eddy currents. It doesn't make any loops of current in here. Hence, no effect. This one here, you have the changing magnetic flux. That's going to induce a current going around a circle that opposes, and then you have the repulsion of the two magnets that throws it off. So those are examples of eddy currents. Now, inductance is a similar idea. This is not a transformer. But if I put another coil like this up above, just put this like this and put another coil right here, it would make it a transformer. Transformers are really kind of simple devices. They're mutual inductors. What does inductor mean? It means that because I had a change in the magnetic flux, I induced a current. So this ring had an induced current in it. A mutual inductor, you have the coil here that makes a magnetic field, and then you put another coil up here that's going to have the same flux as this coil. And so this coil makes a magnetic field. This one feels the changing magnetic field and responds to it. So that's what a transformer is. Of course, if I just connected this to a battery, if I connected this to 5 volts, would that make a magnetic field? It should. In fact, I kind of want to go bring my power supply back out just to do it. It'll create a magnetic field. And if I put like a ring on here, once I've connected up to the 5 volts, if I put the ring on there, what's going to happen when the ring's sitting on there? Will it have an eddy current? The answer is no. When I put it on, during the process of putting it on, the flux is increasing, it's going to have an eddy current. But if I have a constant magnetic field, then it's going to do nothing because the eddy current requires a changing magnetic flux. Not just a magnetic field, not just a magnetic flux, but a changing flux. So if I have direct current connected to this, there's going to be no current in the secondary ring. So you have to have alternating current to make a transformer. Direct current, it's only going to do something the instant you plug it in. and then it stops. Now let's talk about how this works. You're going to have, in the transformer, you have the primary side. The primary side, you put a voltage in, it creates a current. That current then creates a magnetic field. That's the whole thing that's going on the primary side. Create a magnetic field. You use an AC source. So what's happening to the magnetic field if I'm using an alternating current? Sometimes the current's going to the left, sometimes it's going to the right. What's happening to the magnetic field? It's oscillating, it's going up and down, up and down, up and down. So that's the primary side. On the secondary side, I have another coil, and all of the magnetic field created by the primary goes into the secondary. So in the secondary, I have the magnetic flux going up and down, up and down, up and down. And so the output side is going to have an induced EMF minus N secondary times the change in magnetic flux over change in time. Right? That's Faraday's law of induction. But on the primary side, what's my magnetic flux? Mu I times the number of turns in the primary divided by the length of the primary there. So if that's the magnetic field, then over here I'm going to have so that should be the voltage I'm getting out. And then we come to this and we say, well, the voltage I'm getting out is going to be proportional to the number of turns in the primary times the number of turns in the secondary divided by the length of that primary, and then times the rate at which the current is changing. What if the current is constant? Then what's the voltage output going to be? It's going to be nothing. If delta I is 0, then the voltage out is going to be 0. So this, once again, only works if the current is fluctuating. Now, what I did here was kind of a simplistic version because I didn't include things like the resistance in the coils and whatnot. So my answer is a little bit different than what you would get with a traditional a full and complete analysis. But here's the end result for a perfect transformer. For a perfect transformer, voltage 1 over voltage 2 is equal to the number of turns in loop 1 over the number of turns in loop 2. What I had was a relationship between current and voltage. Here it's between voltage and voltage. So let's say that I'm here in the United States and we use 110 volts for our electric power. And I go to Norway. Did this last summer. It was awesome. Stayed at my relative's house there. If I want to use something that is not already built in to work in either 110 or 220 volts, if I were to just plug it into the wall, it would have twice the voltage that I want. And so back when I was in college, we went on a choir tour to England. And actually, your aunt was on the tour. And one of her good friends had a transformer, but you had to plug in different pieces for different voltage things, and she didn't do that. She just put the transformer in without putting one of the actual transformer things on there. Ended up that she connected her 110 hairdryer to 220 voltage. If I double the voltage and I keep the same resistance, what's happening to the power? Power is V squared over R. So if you double the voltage, what happens to the power? 4 times higher. So what happens to her hair dryer? It melts, right? Because she had too high a voltage. She needed a transformer to step the voltage down to half of that voltage. So what she needed was, that's what she needed. The voltage 2 is 1/2 of voltage 1. But if we use this equation, voltage 2 is equal to voltage 1 times N2 over N1. So what she needed was a transformer with N2 over N1 equals 1/2, or N1 is equal to 2N2. If she had that situation, then it would have cut the voltage from 220 to 110 and everything would have worked properly. So that's what you need to have when you travel to a foreign country if you have a device that's not made to operate on their voltage. And like I said, back when I was in college, nothing was. These days, we were pleased to find out that my computer and our iPhone chargers and even my wife's, I think, curling iron worked with either way. So it wasn't a big problem with the voltage difference. We still had to make the plugs fit, but that's cheap to buy something that will just adapt the size. But a transformer, the primary job of a transformer is to allow us to step up or down the voltage. But if you step up or down the voltage, you don't create something from nothing. So the power in ideally is equal to the power out. Why did I say ideally? Because sometimes you have efficiency that's less than 1. That is, the power out is less than the power in. But in an ideal case, they're the same. For electricity, voltage 1, current 1 is power in. Voltage 2, current 2 is power out. So I should have voltage 1 over voltage 2 is equal to current 2 over current 1. And since voltage 1 over voltage 2 was equal to N1 over N2, then I have really 3 relations there. Well, yeah, 3 relations. Relation between the currents, between the voltages, and between the number of turns in each one. Or same thing I wrote right here. So for transformer, if it steps up the voltage, what's it going to do to the current? If voltage goes up, the current goes down, so the power stays the same. And that's in an ideal transformer. So here's a question that I pre-warn you most students get wrong. What is the output voltage of a transformer with N1 is equal to 100 volts, or no, turns, N2 is equal to 200 turns, and V1 is 12 volts DC? It's a tight one. Wait for Gila to break the tie. Oh, and Brittany. Gila and Brittany. It could end up in a tie still. Oh, they went. Oh, somebody changed their vote. That's what happened. Okay. There you have it. 10117. Yeah. You know what? I'm going to give Corso another chance.
Do someone else. It's fine.
This is to help you, Corso.
It's fine. It's okay. Do someone else. I got it wrong.
No, you got it right.
I did.
Yes.
I guess.
Yes.
I put 0, but
Well, okay then. Rebecca.
Okay, well, I put 6 on D, 6 volts.
Okay, she put 6 volts. Why?
Because if you have twice the amount of and you think it will like cut it in half.
Okay, we had V1 over V2 is N1 over N2, right? V1 over V2 is N1 over N2. So you would say V2 is equal to V1 times N2 over N1 equals 12 volts times 200 over 100. So most people, I know this isn't what you said, but most people would say 24 volts. But they would be wrong and Corso would be right. Why are they wrong? It's important because this is about thinking and not just using math. One person said 0 volts, that was Corso. So since Corso said he guessed, we were all wrong.
I wasn't wrong.
Well, none of us knew what the answer was, okay? Erika.
Didn't you say that if volts go up, power goes down?
Yes.
So wouldn't that be?
Or actually said volts go up, current goes down. Here's the key that you have to think, not just use math. DC. What is the output if you put DC into a transformer? It's 0 because the transformer requires a change in flux. Our work up here, we had as a key for the output voltage the change in flux. If it's DC, that's 0. End of problem. Doesn't matter how much voltage you put in, there's no change in flux, there's no output. There's a flux, just not a change. And so the question here, the correct answer was 0 because it was direct current. And I have put this on the test before. It's just a simple, do you know what a transformer is? Not can you do math, do you know what a transformer is? If you know what a transformer is, you get the question, no time spent. If you don't know what a transformer is, you spend a little time and then get the wrong answer because instead of thinking about it, you were just trying to do math. Now, I do have a follow-up question, which is kind of lame because I went and did the answer for you. What is the output voltage of the transformer if you change it to AC? We had 17 that said 24, one that said 6 volts. I just worked it out. Right there, 24 volts. Not sure how we got 6 volts after we just worked it out, but
It's not.
it wasn't Corso. No, it was not Corso.
I didn't get that.
Power delivery. we get 120 volts in our homes. If you go out and you look at the high voltage lines, we call them high voltage lines for a reason. They're not 120 volts. I should point out, I said we get 120 volts in our homes. That's not true. Anybody here know what we get in our homes? It depends on the time of day. They actually vary the voltage a little bit. Because when there's a high demand, they lower the voltage a little bit so that their power supply lasts longer. That is, they can supply more people power with a slightly lower voltage. They have a bigger, well, a smaller power that people are going to use. And so it actually varies. And so some people say 110, some say 120, some say 115, because it does vary. Nominally, it's 120. If there's no special demand on the power, you probably have 120 volts. But those high voltage lines are going to be somewhere in the ballpark of, let's say, 350,000 volts. Why in the world do you want to have 350,000 volts out there? I mean, what happens if I lick my fingers? Okay, I don't have to lick my fingers for anything important to happen. And I grab a wire that's 350,000 volts. Yeah, I die, right? It's the old Farmer John's pumps when you cook them thing, right? It's a bad deal. So why do they do that? Answers. What's the only answer that would make sense? And no, it's not to kill people dead. Well, it is in large part because of the long distance lines, but it's not because they're going to have a big voltage drop. If that's what it sounds like you're saying. It's not because of a big voltage drop. In fact, when they have 350,000 volts, they're going to have a much bigger voltage drop on the line than they would have if they'd had, a smaller voltage. What is the big concern for the electrical power company? Money? What do you say? Not to lose it. Not to lose it. Well, you have wires, and these wires are not superconductors. That means they have a finite resistance. There's energy lost as electricity goes through those wires. But the power lost is going to be current squared times the resistance of the line, right? Because you have the current going through the wire. And so how can I keep my power lost as small as possible? What do I can't affect the resistance in the line pretty much. That's the wires. I try to use low resistance wires, but I can't get over that. So what do I want to do to lower the power that's lost in my transmission lines? Do it. I want to decrease the current, but I still need to deliver a power, a certain voltage times current at the end. So I want to deliver a lot of power, but with low current. Well, how can I deliver a large power, a VI, with a low current? I boost the voltage way up. And so by raising the voltage, you have a lower current, and thus you have less loss in the transmission lines. And it makes a difference of, we could do the calculation, but it makes an enormous difference in the efficiency of the power lines to have a high voltage rather than low voltage line. And we could do the calculation, but because we're out of time, we won't. Final thing for today, self-inductance. Joseph Henry, he lived in the 1800s, came up with something about self-inductors. What's a self-inductor? Well, we just talked about transformers, mutual inductors. A mutual inductor is when I have a loop, a coil, and then I have another coil, and they share the same magnetic field. So that's a transformer. A self-inductor has a coil, the end. And what you're looking at is the induced voltage created in the coil by the changing magnetic field, the changing flux that it itself created. So we take the same ideas that we apply to the mutual inductor. Oh, look, somebody's getting some flowers. Dr. Seth McNeil bringing flowers for, I assume, Dr. Crane McNeil. I mean, it could be for me. Who knows?